All right, AP, let's take a look at a couple of the exercise problems. Here's number 5 that we have. And one thing I recommend when doing these, it's really helpful if we draw a picture. As you do more of these, the pictures might not be necessary, but the nice thing about drawing a picture, it always makes you understand which way the energy is flowing. And energy flowing is really important because if you get the direction of it wrong, usually that leads to either putting a positive or negative symbol somewhere, and you may have the right answer, the right absolute value, but you'll have the wrong sign on it. So I always like to look at these first from the standpoint of a diagram, and then dissecting the problem and figuring out what I need. Um, all right, so let's read through this problem. In a coffee cup calorimeter, I have 100 milliliters of NaOH, or it's in 1 molar. So here's my coffee cup. Okay, my walls are insulating it, keeping what's inside energy inside, what's outside energy outside. I've got 100 milliliters. Okay, and remember 1 milliliter equals 1 gram, so I've got 100 grams of H2O. And what is in here is NaOH, and I'm going to add another 100 milliliters to that, so we're going to go up top. All right, so my total, here's another 100 milliliters, another 100 grams, and that's HCl. Now, obviously, they're not going to be separated like that. I'm just doing this as I'm thinking through. So I've got 200 milliliters of NaOH plus HCl. And at this point, what I like to do is I like to totally think about this problem and going, okay, this is a base, that's an acid, this looks like a neutralization, and I have equal parts. I've got, this is 1 molar, this is 1 molar, and I've got 100 milliliters of each. All right, so I've got the same quantity of each, and this is in the reaction form a 1 to 1. So I'm going to form Na ion, okay, and chlorine ion. NaCl is soluble in water. It will not form a precipitate, so it'll just stay separated. Plus, I'm going to form a whole bunch of new water. Okay, so what we're trying to see here is how much energy is released from this chemical reaction. Okay, um, and so as we set this up, we want to calculate the value of Q. Okay, Q equals thermal energy or heat. And as you can see above on here, Q equals MC delta T. Okay, and this C stands for the specific heat capacity. And in this case, because we are doing this in water, we're going to use the specific heat capacity of water. So Cp of water equals 4.184 joules per gram per degree Celsius. Okay, M equals the mass of water in the coffee cup. And so in this case, we have 100 grams or 100 milliliters plus 100 milliliters. So this is 200 grams. All right, and delta T, or the change in temp. Okay, so let's continue to look at this. It says both the solutions were originally 24.6 degrees Celsius. Okay, so I've got 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius. So delta T equals final minus initial. So my final temperature is this 31.3 degrees Celsius. And I'm going to subtract the 24.6, which was my initial temperature, to get my delta T. So my delta T, after I plug and chug here, is 6.7 degrees Celsius. Okay, once again, this is the final temp minus the initial. Okay, just like all of our setups are for deltas. Okay, so now we have all of our pieces here for our formula. We have the mass, we have the specific heat, and we have the change in temperature. With that, it's fairly simple to plug and chug this in, as you guys are used to doing in physics. Q equals 200 grams times the specific heat, which is 4.184 joules per 1 gram per 1 degree Celsius. And we're going to multiply that also by our change in temperature, which is 6.7 degrees Celsius. Okay, and our temperature is going up. Okay, um, so let's look at what we have here. We've got Celsius dividing out Celsius, grams dividing out grams. We're going to get our answer here in joules. Okay, and so when we calculate this through, we get 5,606.56 joules, and or 5.6 kilojoules. All right. Um, Now, we need to ask ourselves, is this energy entering or leaving the system? Let's go back to the question here. So it says, assume no heat is lost to the surroundings. Let me pull that down of the calorimetry. Okay, so we did that. That's why we have the coffee cup. We're not losing anything to the outside of the cup. Calculate the enthalpy change for the neutralization. Okay, so how much energy is our system losing? Our system is our chemical reaction. This here, sorry about that. This is our system. The NaOH HCl reaction is our system. So how much energy is it losing? Well, it's losing 5.6 kilojoules, and that's moving away. So that means that this is going to be negative change in enthalpy. Okay, the change in enthalpy for this system is negative 5.6 kilojoules. All right, the negative sign here indicates that this is the energy leaving the chemical system. Okay, so negative 5.6 kJ is leaving. Okay, box our answer, make it easy on the test grader, and we're on our way.